Okay, so the next question is then maybe considering how in the world do we figure this out in a lab? And so the way that we figure this out in a lab is that we would take a sample of our material. So for example, let's say this was the penicillin. And I can put it basically in a container in a furnace. And it's going to go through combustion. And so this is where we're basically breaking it down with heat and with oxygen being in there. And then it's going to go through and turn into carbon dioxide and water, and it might turn into a few other gases, okay? But basically what we do is we collect those along the way. So we have something that will absorb the water, we have something else that will absorb the carbon dioxide, and then the other gases would get vented out. And so what we are doing is we can figure out what's the composition of that compound by then knowing how much carbon dioxide, how much water, how much other stuff is produced. And so what we then want to do is find the empirical and molecular formulas. The empirical formula is the smallest ratio. So this is an important definition to know. The empirical formula is the smallest ratio of the elements. We need to know the molar mass to determine the molecular formula, which is going to be basically the empirical formula mass multiplied by some integer, okay? So the molecular formula is always a multiple of the empirical formula. So when we determine empirical and molecular formulas, sometimes we do that with things that are considered hydrates. So they have dot waters. Essentially, they're water molecules that are used, that are associated with their crystal structure. So for example, copper sulfate is a common hydrate, and we would show that it has waters associated with it by writing a dot and then how many waters are associated with that crystal structure, okay, with 1 unit of that. And so in this case, we would call this copper 2 sulfate pentahydrate. So we'd use those prefixes like we would normally use with covalent compounds and then say that it's a hydrate. If something instead is anhydrous, it means that it's without water. So we have gotten rid of all of the water there. How would we use the information from an experiment like this to determine the empirical formula and potentially the molecular formula of the compound? Well, let's take a look at an example. So the important part for this is that we're going to be looking at percentages, but if we look at percentages and just assume that we have 100 grams, then we can turn those percent signs just into grams and then convert to moles. So you will see a little information here relating to determining that empirical formula. It's really the steps that we've talked about. And again, as a reminder here, molecular formula is a multiple of the empirical formula. And why do we even have that? Well, sometimes that's the way things will occur in nature, or there may be multiple forms of things. So the molecular formula might be the one that we find more naturally. This especially happens with covalent compounds. And but the empirical formula is the one that I determine based on that, for example, combustion data. So let's do a problem together where we are finding both the empirical and molecular formulas. Given this data, we have percentages for each, and we know then the molar mass of the compound ends up being 98.96. So the first thing that I am going to do is I am going to convert really my percentages into grams. Okay, we just have to change the label. And then I'm going to convert that into moles. So take a second, pause the video, and try doing that. So you should have calculated these number of moles, and now what we're going to do, so my first step was to do this conversion. My second step then is to divide by the smallest. So divide by smallest number of moles. And so this is 2.021 for each of these. 2, 1, I should say. And so the first two, I get 1 to 1, and then I get a 2. And so in this case, I now know that my empirical formula has the formula CH2Cl. Now you may be saying, like, why did you write it in that order? Well, usually we write things in order from lowest electronegativity to highest, and so chlorine is the highest electronegativity. If you didn't write that way on the test, that's fine. I'm not worried about that, and they won't really worry about that at AP. It's just looking for the correct ratio. So the last part then is, how do we figure out the molecular formula? Well, we know the molecular formula should be a multiple. So the molecular formula mass divided by the empirical formula mass should give us that N value, that multiplier, okay? And so in this case, we know that the molecular formula mass is 98.96 grams per mole. I can add up the empirical formula mass from the empirical formula I just found, and so that is 49.48. I'm running out of room here. And that ends up being then 2 when I divide those out. So my molecular formula should be double my empirical formula. So my molecular formula should be C2H4Cl2. Okay, and so that's how we do that to figure out empirical and molecular formula. Let's go ahead and try another example. Why don't you take a second and try this one on your own? It only has 2 elements in it, so see if you can get to the correct answer. Pause the video, try it, and then see how you did. So hopefully you got this far and were able to get the ratio of 1 to 2.5. Well, wait a second, how do we deal with that? Because we can't have like half an atom or something like that. Well, what we're going to do is take those, and if they end up being something like a half, we're going to just double that so that we end up with 5 then, and we're going to do the same to end up with 2 then for those two different things. So in this case, my empirical formula would have the formula P2O5. To find the molecular formula, again, I'm going to take the mass that was given there. So I'm going to take that molecular formula mass, divide it by the empirical formula mass in order to get that multiplier. So my top is going to be 283.88. My bottom is going to be 141.94, which gives me a multiplier of 2. So that means that my molecular formula is then P4O10. Okay? So we've now found the empirical and molecular formula. Let's try another one. Take a look at this one. We're going to determine the formula of caffeine. Let's try this one on your own. Again, pause and then check your answer. Okay, so you should have hopefully again found the same answers, the same ratio that I did. So our empirical formula, again that lowest ratio formula, is C4H5N2O. We need to find our molecular formula, so we're going to take that mass that's given in the problem. So we're going to take the 194.2 grams per mole. We're going to divide it by the empirical formula mass, which if you add that up is 97.11. Oops. And so our multiplier is really 2. And so my molecular formula, let's see if I can squeeze it in down here at the bottom. Actually, I'm going to squeeze it in up here at the top. My molecular formula is C8H10N4O2. Just double it because of our multiplier being 2. So that's how we figure out the formula for different things, whether it's the empirical formula, the lowest ratio, or the molecular formula instead.